we're going to learn about reaction mechanisms. It's our last lesson in our unit on energy and rates of reaction. So what we're going to do today is try and put together some concepts that we've learned about energy, enthalpy, potential energy diagrams, reaction, collision theory, and rate law. So, what are reaction mechanisms? They're things that help us study how a reaction proceeds. How do we go from a reactant to a product? And there's often many steps that happen on a molecular level that we don't see. So to try and give you an idea of what this means, we're going to look at an example of how chocolate is converted from cocoa beans into the chocolate that we eat. So we start with cocoa beans and get something like a caramel bar. Are there many steps in between? Definitely. So let's take a look. What happens first? You have to clean off those raw cocoa beans. You wouldn't want to eat those. They're very bitter, they're not cooked, they're not roasted, they don't have a good flavor. So those are some things that you need to do first. They go through many processes, cracking, changing the pH, adding in different things like sugar and milk. Then there's refining, tempering. Some of it goes off to make liquid coatings, or maybe chocolate chips, or molded into chocolate bars and then sent off for distribution. We don't see all of those things happen. We just know chocolate comes from cocoa beans. So chemical reactions kind of act the same way. We know what reactants go in, we know what products come out of the reaction, but how does it actually take place? So that's what we're going to look at today. So when you're looking at a reaction mechanism, there's two main things that you want to look at, whether you're coming up with one, whether you're studying one, seeing if it's valid or not. So the two things are, one, the elementary steps, and two, the rate determining steps. So what are elementary steps? These are simple little chemical reactions that happen throughout the process. How many elementary steps can you have in a mechanism? It depends on your mechanism. Some can have 2, some can have 3, some can have 4, some can have many. That all just depends on your reaction. The second factor is something called the rate determining step. The easiest way to think about this one is it's going to be the slowest out of all of the elementary steps. So this one's used to help us figure out things like the rate law and the overall rate of the reaction. So we're going to first take a look at elementary steps, and then we'll spend some more time on the rate determining step. So elementary steps, what are they? In a nutshell, they're a series of very simple reactions that are trying to show us how the chemical reaction proceeds, but we want to know on a molecular level. So what atoms or compounds are involved and what's going on. So down here we have an example of a very simple reaction mechanism. At the top, this is our overall equation that we're trying to study, and we want to figure out how do these reactants make this product. 2 moles of nitrogen monoxide and 1 mole of oxygen gas. How do they combine to give us 2 moles of nitrogen dioxide? So someone has proposed that this is a 2-step process. In step 1, 1 mole of nitrogen monoxide combines with 1 mole of oxygen gas, and this makes nitrogen trioxide. Now wait a minute, nitrogen trioxide isn't in our overall equation. Don't worry, we're going to take care of that in a minute. In step 2, you can see here's that nitrogen trioxide again. It's going to react with the 2nd mole of nitrogen monoxide, because we have 2 of them up here. It's going to react and give us our 2 moles of nitrogen dioxide. That's our product. So how do you go from 1 step, 2 step, and end up with your overall equation? Let's see what happens when we add them together. So we take all of our reactants, put them over here, nitrogen monoxide, oxygen gas, nitrogen trioxide, another mole of nitrogen monoxide, And our two products, nitrogen trioxide and 2 moles of nitrogen dioxide. Now looking at that, you might think, well, that doesn't really look like my overall equation. But let's go back to that nitrogen trioxide for a minute. It's present on both sides of the equation. That means that we can cancel it out. It's not going to be there anymore. But then you might think, well, it still doesn't really look like my overall equation. But that's because the nitrogen monoxide is split up. There's 1 mole here and 1 mole over here. So if we were to combine them, we would get 2 moles of nitrogen monoxide. There's our oxygen gas. And guess what's left on the other side? Are 2 moles of nitrogen dioxide. So those 2 steps do add together and give us our overall equation. Now what's going on with that nitrogen trioxide? It's called a reaction intermediate. One step produces the compound, and then it's consumed immediately in the next step. So it appears and then disappears. Depending on how many steps you can have, there can be multiple reaction intermediates, sometimes 2, sometimes 3. Other things you might notice in the elementary steps, if there's a catalyst involved, you might see that show up in your steps, but it's a little bit different. You'll notice the catalyst goes in one step and it'll come out in the other. Because catalysts we know are used, but they're not consumed. Next, let's take a look at the rate determining step. This one's your slowest elementary step. And this is important. How do you know which one is slow? When you're given a problem with different steps at this level of chemistry, it'll tell you whether it's a fast step or a slow step relative to one another. So don't worry about that for now, and in our next example we'll take a look at where that's indicated. But the interesting thing is this is going to determine the overall rate of the reaction. So all the information about the rate of the reaction, whether it takes place in many steps or just a couple, is all determined by this slowest step. How do we know? There's a couple ways of looking at this. One is to look at the activation energy, and the activation energy for this step is going to be higher than the activation energy of all the other steps. We can see this on a potential energy diagram, and we'll see that in our next example. How do you really understand what's going on? A good analogy is walking with grandma. So my grandma, when she was older, was really slow walking, but whenever we went together, we had to make sure we stayed together as a group. So let's say you're going out for dinner with your grandma, and you're walking out of the car and going into the restaurant. Doesn't matter how fast you are or how hungry you are, you could sprint into the restaurant and you're going to stand inside and wait, and you're going to wait until grandma walks slowly all the way up to the door, or you can walk with her and walk into the restaurant at the same time. Doesn't matter how fast you can go, you're still going to have to wait for grandma to get into that restaurant before you get a table, sit down, and have your dinner. So thinking about walking with grandma is a good analogy to try and understand what's going on with the rate determining step. The other steps can go as fast as they want, but if one is lagging behind the others, that's going to determine how fast or slow the reaction actually proceeds. So here's another example of a proposed reaction mechanism. We have a big overall equation up at the top here. And this time there's 3 steps that are proposed for this reaction mechanism. Step 1, step 2, step 3. But what's different this time, now we have some indication about the speed. So here in brackets we have fast for step 1 and 3. They're faster compared to step 2, which is indicated as slow. If you see slow here, this is telling you this is your rate determining step. That's your slowest step. How else can you tell? Well, you can look at your potential energy diagram. So down below here, we've got that diagram. Let's do a quick review. Y-axis is your energy, often labeled as potential energy, and we know we're looking at kilojoules. On the x-axis, you have your reaction progress, how the reaction proceeds from reactants to products. We still see our reactants and our products listed, and we know the difference between the two. That's going to give us our enthalpy, or a delta H. So that hasn't changed with this type of diagram. But what you might notice, something that's different, is there's more than one hill. So far we've only seen one hill in our potential energy diagrams. So there's three. First hill, the second hill, and the third hill. So what's going on here? Guess what? Each one of the hills matches up with one of the steps. Step 1 up here matches with hill number 1. Step 2 matches with hill 2, and step 3 matches with hill 3. So how can we use that to figure out what's fast and slow? Well, let's take a look. Let's look at activation energy. The difference here, activation energy 1 compared to activation energy 2. And then we've got another one here, activation energy 3. Visually, you can see the largest hill belongs to number 2, step 2. And that should make sense. If it's the slowest step, it's going to require the most energy to get all the way up to that activated complex in that transition state. So when we look, activation energy 2 is definitely going to be bigger than the others. It's the largest, followed by activation energy 3, and then 1. So we know here activation energy 2 belongs to the rate determining step. So visually, that's another way you can check which step is your slowest step. Let's say you weren't given these indications of slow and fast, but you were given a profile. That's one way you can figure out the slowest step. Finally, how does this all relate to rate law and rates that we've been studying? So this is pretty interesting. Experimentally, they found the rate determining step decides the rate law for the reaction. This only works here with elementary reactions and only works with the rate determining step. So if we take another look, here, step 2, we want to write the rate law. So remember, rate law has a rate law constant K, and it's only going to look at your reactants. So for step 2, we only care about step 2. Here's our N2O2. And just like before, we put it in square brackets. Then we're going to put in our H2 in square brackets. And then what happens with the exponents? Here, with your rate determining step, as an elementary step, it becomes the exponents for the reaction. So here we've got 1 for our coefficient for balancing. That's going to become our exponent. We've also got 1 for coefficient for balancing for hydrogen gas. It also becomes our exponent here. So here, your exponents match the coefficients. And this is only for elementary steps. So they found that if you're studying the rate law and you come up with a rate law for reaction, it actually matches the rate determining step, which is pretty neat. The other thing we can look at with this example are the reaction intermediates, because we didn't do that before. So this is a 3-step process, and there's actually a couple of reaction intermediates. Here in step 1, we get N2O2 being produced, and then guess what? It gets consumed. So here, this is one reaction intermediate. Then let's take a look. Is there another one? Definitely. Here's another one, N2O. it gets produced, and here it gets consumed. Both of these do not appear in your overall reaction, but they're important to understand the process. But here we know these are our intermediates. So if you're evaluating reaction mechanisms, part of your homework, there's a couple things you can check. First thing that I would do, make sure all of your steps add up and combine to give you your overall equation. That would be first thing that I would check. If the steps don't make sense, then the whole mechanism won't make sense. Once you've done that, then you want to look at each individual step. Is it plausible that this can happen? How many reactions do I have? 2, 3? That's probably likely that those reactions will happen. But if your steps have maybe 4 or 5 reactions in them, it's probably not going to be very plausible. Then there might be some questions about the rate law. So if you can figure out which one the slowest step is, or match it with a given rate law, that'll also help figure out, is this reaction mechanism actually make sense or not. So hopefully this helps understand a little bit more about reaction mechanisms. And please post if you have any questions on the discussion board.